Welcome back to our lessons on chemical equilibrium. Today I want to start on chapter 15. It is a chapter on equilibrium constant, and we're going to look at definitions and examples. So, what is the equilibrium constant? The symbol Kc is the ratio between the rate of the forward reaction and the rate of the reverse reaction at equilibrium. Therefore, the temperature must be constant. Just to inform you, at this point in time, you can only have an equilibrium situation if the temperature of the system is kept constant. Your textbook on page 185 says that it's the expression of mass action, most probably because a ratio of concentration of something over concentration of something else, let's say concentration of X over concentration of Y, where concentration is mole divided by volume, and so it's moles of X divided by moles of Y over V, where your volume is the same for each reactant. So basically it's moles of X over moles of Y. This is a simplified expression, and moles is basically mass over molar mass divided by mass of Y over molar mass of Y. So that's most probably why the textbook says it's an expression of mass action. So let's look at an example. We've got nitrogen dioxide in equilibrium with dinitrogen tetraoxide. 2 moles of nitrogen dioxide forms 1 mole of dinitrogen tetraoxide. We know by now that nitrogen dioxide is a reddish brown or a brown gas, where dinitrogen tetraoxide is colorless. So at equilibrium, the rate of the forward reaction is directly proportional to the concentration of the nitrogen dioxide. But because we have 2 moles of nitrogen dioxide, we have nitrogen dioxide's concentration times nitrogen dioxide's concentration. So basically it's the square of the concentration of nitrogen dioxide. So your coefficient to the number, this is the coefficient to the substance, becomes the power of the concentration. And the rate of the reverse reaction would be directly proportional to the concentration of dinitrogen tetraoxide. So the Kc value is the ratio between the concentration of the product on the right hand side divided by the product of the concentration of the reactants on the left hand side. So this is a simple example showing us how to write Kc expression. Hypothetically, we have A amount of reactant A reacting with B amount of reactant B, and it's in equilibrium with C moles of reactant C and D moles of reactant D. It's at equilibrium, so the temperature must be constant. The expression for this, so Kc is the ratio of the concentrations of the products. So you have the concentration of C to the power C, the concentration of D to the power D, divided by the concentration of A to the power A and concentration of B to the power B. So this is the hypothetical expression for the equilibrium constant. The following facts are things that we need to know. First of all, Kc has no unit because it is a constant ratio between concentrations. So therefore it has no unit. Second thing, the reaction equation must be balanced for us in order to be able to write the Kc expression so that the powers of the concentrations will be correct. Thirdly, C stands for concentration, so it is measured in mole per cubic decimeter, but Kc is the ratio between concentrations, so it's got no unit. The square brackets, we know by now from last year already that it means equilibrium concentration or just simply concentration. The fifth thing, only concentrations of gases and solutions are used, as the concentration of solids and pure liquids cannot change. And the last point is the Kc is independent of reaction mechanism, so a catalyst will not affect Kc. Pressure will not affect Kc, concentration will not affect Kc, as they are usually constant ratios at equilibrium, but temperature affects Kc. So what is the meaning of Kc when we look at the chemistry behind reversible reactions? If Kc is equal to 1, the concentrations of the products are equal to the concentrations of the reactants. If Kc is much bigger than 1, that's why I've got those mathematical operators there, the equilibrium lies to the right. It means that the concentrations of the products are higher than that of the reactant. So your numerator is much bigger than your denominator. If Kc is much smaller than 1, the equilibrium lies to the left. What does that mean? The concentrations of the products are lower than that of the reactants. So let's put some examples in here. We know that hydrogen chloride is a strong acid, so when it is mixed with water, basically all the hydrogen chloride molecules will break up to make hydrogen ions and chloride ions. So most of what you will have in the container at equilibrium will be hydrogen ions and chloride ions, and you'll have very little molecules of hydrogen chloride. So the equilibrium lies to the right, and I symbolize it using a longer arrow that points to the right than the other arrow. Still in equilibrium, but the equilibrium lies to the right. It's not important to use that type of arrow. It's just my way of explaining. On the other hand, if we look at ethanoic acid, CH3, COOH, if this liquid is mixed with water, very little of it will ionize. Most of it will be the molecules CH3COOH intact. So you'll have a very small concentration of hydrogen ions and ethanoate ions. I hope that brings us into understanding the basics around KC. See you in lesson 2, the next lesson.